when I reach this page, okay, so people treat this very lightly, okay. Don't take a close look at what I'm going to describe. And actually, I usually stop for around 5 to 10 minutes over this single page, okay. So no matter how sleepy you are, wake up and listen to this page, okay. This page is, I will say that it's core, really the core of this part as well as the implementation of the scheduler. Okay? So you will be asked the following questions. Okay? The following questions are, so you know, you have, I start when it is week 1, okay, I tell you there are illusion about scheduler or about operating system. What is this illusion? The illusion is about you are having a computer sharing different processes over or only CPU. Maybe you have one or many, it doesn't care, okay? Because you have a far more amount of processors that run on the CPU. Now, I tell you the illusion is that you are doing a time sharing system. So what is time sharing? At a specific time, that CPU is occupied by exactly one process, and then for some time later, we will switch. Okay? So my question is, do you find any code in your process that tell the CPU that, hey, I don't want a CPU? No. You never find it. You just type your code, you type your for loop, I don't know how many layers, you use your printf, you use your recursive to terminate the process, but never says that I want to give up the CPU. So that means that, yeah, keep it in your mind, okay? That means that the control of this time sharing system or time sharing implementation is not on your side. It's on the kernel side. Okay? Kernel takes control. And you never know, right? You never know that, I'm doing an A plus B, so it should be C equal A plus B, right? Then while you're doing this, suddenly you will have a chance that the kernel say that, okay, this is the time that you have to stop. Finish the C equal A plus B, and then give up the CPU, I will schedule another guy. The working is like that, okay? And this is how, I mean, this is not how, but this is not the exact implementation, but very close to it. The CPU will get interrupted by the kernel. I consider that kind of interrupt here, this guy, clock, okay? We have the clock. And actually the clock is the hardware clock that last time I talked about while I was illustrating the idea of the alarm system clock, okay? Oh, sorry. Just take it. Okay. So this is the alarm, or you can treat it as a kernel space alarm. Okay? In last time, why I keep talking about the alarm and didn't ask you to use it in assignment or no main sample code there, because the implementation is also happening inside the kernel. Yeah, you set up an alarm. Let's say when the kernel scheduler knows that, okay, I have 10 processes here, I don't know how many processes. Let's start with this process, okay? I ask this process to run, and in the beginning of the run, okay, I still get the CPU access. I'm the kernel, okay? Here's the process. I set up an alarm and then switch the CPU to his code. That means that I give up my privilege in using the CPU. I give him the code. I give him the chance to put the code on the CPU. Now he is running, but at the same time I set up an alarm. Okay? And when alarm trigger, we're gonna fire, the alarm fire, then he will get interrupted just like the alarm system call. Just like alarm system call. And who is the handler? Me, the scheduler. The scheduler is the handler. Okay? When the handlers of the alarm step in, he is not being terminated, okay? Yeah, he's still here. And I will step in and say that, okay, you go to a suspension stage. I try to schedule another guy. Yeah, I treat you as a process. Okay? Process P. Okay. Then we will go to another process. Okay? So this is one of the implementation that I cannot draw exact picture here, but just give you an icon here, the clock. Okay, and in a real implementation, it is very similar to what I just said. Okay, it's set an alarm clock, and next thing you will expect there is a periodic alarm clock, right? This guy, the P1 finish executing, and then I went P2, P3, P4, and maybe I only 4 processes go back to P1, okay? And I will have this periodic alarm keep firing, and so that I'm a handler, I'm a scheduler, I will try to set in and schedule the stuff. Okay? So this is why I said that this page is very important, because this is one of the sources that scheduler will step in. Okay? And the second chance that the scheduler will step in is that guy, a particular process, okay, go to some other task. What is the task? The task is, I illustrated before, this area, the block state. Okay? They enter one of the block state. I don't know which. Okay? Maybe the interruptible means that you are doing scan F, waiting for a keyboard input. You open a file or a copy called F open. Okay? And you know copy is slow. Okay? So in the meantime, when you do the interruptible block state, okay, the CPU is still there, okay, you are supplying power to the CPU, but will the CPU serve you? No. Right? You are waiting for the keyboard input. And for good implementation of an operating system, at that moment of time, we shouldn't let the CPU idle. Okay? We let the CPU to serve other guys. So this is another trigger, which is very implicit. You never sense that while you are doing the scanf, actually the CPU is doing other things. Okay? Because you have the illusion that you're being served. But no. Okay, you're not being served. The servers will go to the other process. And this is another trigger, we call it block state or blocking system call trigger. Or another one is not blocking system call, but you call the system call exit. You want to die. Okay? When you die, okay, but without the periodic clock signal coming in, okay, let's say the periodic signal clock is 1 second, but you die just because your program stops, okay, you implement some addition force there, okay, and once it's run, it's done, okay, you still have a 0.999 seconds left. What will happen? Because it's part of the system, a kernel code, because system code is a kernel code, right? So I am a scheduler, I know that, oh, you execute that call. Maybe this is the time I step in, okay, to select another process, maybe process P2 again, because this guy has finished waiting for the past this service. And changing from the interruptible block state back to the ready, so then I will be able to pick the cycle. Okay? So that is the scenario, and this graph is, an illustration only, okay? Drawn by the viewpoint from the CPU, okay? When the CPU look up, who is running over me, okay? We will see there's a quickly switching from one process, and then suddenly go to this scheduler. Now, after one process is go to the scheduler, okay? So this area, and the scheduler select who is the next lucky guy, and then I find another lucky guy, and then suddenly this guy goes to call scanf, okay? Then scheduler step in. Okay, so this is the viewpoint from the CPU. Alright? And this is a very important concept that you should not forget. Okay, because even your iPhone, okay, or Android is all based on this kind of scheduling. Okay, but of course their interrupt type will be different, okay? Maybe the input, okay, is a touch screen instead of a keyboard, but still you can call this interrupt block state because you are calling system call. Maybe this is not a scanf, but I don't like Android or iOS, but some input, okay, still will be blocked, okay? And this is the scenario. Now when you think about it, if you know this scenario is happening, you get the illusion that every process runs parallel. Okay, this is an illusion, and they are switching very quickly. When you have some process like that, you're reading from hard disk, basically you won't stop another guy doing sorting over a memory, okay? You're doing something in memory, you need I/O servers. Yeah, you understand what I mean? Doing something over memory, so you don't need I/O servers. You have to understand? Because you're purely working on the memory. It is not reading from a file or writing from a file, so you won't have a chance to block. Okay? So that's why your data structure assignments, if you can still remember the data structure assignments, we seldom ask you that, oh, while we're doing this coding and get some of file inputs and so on. Usually we'll have a bunch of time-doing memory-based operation without any block. And after finish of that, then you can do idle things, and idle things usually start very slow. Really start. And then you go on and until you power off the machine. All right? Any question you want to ask? Or any special experience that you have experienced that I say something wrong? Yeah, you find that, oh, you have seen something wrong, my experience is different. Okay? So either you're using thoughts, okay? You're using thoughts, okay, that's another thing, okay? I consider it as a modern operating system, right? No? Alright? Okay. Good. So what is the switch? Okay, the switch actually has a name. Okay, where is the name? Oh, here. Context switching. Okay? The context switching is a switch. Okay? So you will be curious that hey, switch. Why we call it context switch. Okay, so because the context switch has more than just changing the code execution. Okay, so when you have a process running, okay, now we make it more complex now. I give an execution order here. Let's say originally your program counter inside a CPU, which should be called EIP, I remember. Okay, so EIP, the register called instruction pointer or program counter will point to the user space memory. We already know it. Okay, then when you call system call, a step to sleep is system call, right? Interruptible block state system call. Okay, so when you call it, it will enter interruptible block state. Now, this is the moment that you will switch from one process to another. So how the scheduler will step in? Very easy. First of all, before you go to sleep, okay, we will back up something onto the kernel space. What are the backup? The backup of all the register values. Okay, so you can see this blue guy and the green guy. Okay, so as if we are backing up into a package, and that package will save in the kernel space, just like what? Just like you're switching game in a console a video game player, right? You save something on the same card. Okay, if you don't save it or you don't want to get it throw away the previous progress, okay? So this is just like the same progress, but inside the kernel space, okay? As if you are ready to switch from one process to another. And this is the task of the scheduler. The scheduler will do this. The scheduler looks at, oh, you are going to switch from one process to another, I do the backup. So the kernel space contains many things, not just your PID, your open files, okay, but also now you contain more things, your previous execution states. Okay? After the backup, what it's going to do is inside the scheduler, it will inspect what we call a process queue, a queue of process or process list. Okay, this is not really a first in, first out, okay? It is a process list. You process that list and go from one to the end. Okay, so this is a linear time scanning, okay, which is quite typical, okay, or you have read some books, old books particularly, will say that the linear scheduler, one type of linear scheduler has approximately, not always, of one execution time, okay. We just don't care about the complexity, we just care that the scheduler will eventually take the guy up, okay, and put it on the CPU, load its previous backup on the CPU, and restart the code. Okay? So this is it. This is what we call context switching. Okay? So the context switching, now you don't understand not just the user space memory, not just the process structure. Now we include something more we call the register backup. Okay? Why you have register backup? Because we don't know what is the previous execution. Okay? How many of you have tried what is it called? Intel CPU assembly code. How many of you know? Only a few. Only very few. Okay? So then you will understand that when you look at the assembly code, okay, you are basically working on registers. Okay? And your task, okay, your scheduler, your task will interrupt the program at any moment really, any moment of time. So you cannot expect that, hey, maybe I set up a clock here. This is line 900, okay? Line 900. Now let's stop at 900, and then you will back up for me and do all the things. No, okay? This stepping in of the scheduler may happen at any time, any space, no matter what the code you're running, what functions you're doing, they will step in. Okay? And what is more, this kind of switching will have a bad moment of time that your process, now I can give you a more detailed picture of this picture. Okay? This picture is talking about, still remember in week 1 or week 2, I don't remember. I talk about it when you have a process which is sleeping, I used to call sleeping, right? Sleeping in a hard disk, okay? So what exactly does it mean? This means that you have a bunch of user space memory, okay? How you construct that bunch of user space memory? Manually, right? Or you create a very big global variable, okay? So you create those kind of memory, that kind of memory is here. Maybe your space is too big, okay? Let me show you mirror. I don't know because yesterday I just reboot my computer. I don't know whether we can see this. Memory usage? Ah, okay, good. Good. So you can see this, I have a physical memory of 8 GB. Yeah, maybe yours is 16, okay? Then I have this amount used, okay? And minus this is the free space. And what is this? The swap use. The swap use is back to that diagram. It's this guy. Okay, we call it a swap. Okay, the swap use means that we put some of the memory that used to be a part inside the main memory. But the main memory, I don't know why. Maybe I play some game, I do some a video filming, so that I use up all the space in the main memory. Some part of I don't know which process go to the hard disk, and we call swap. Okay, so that's why when you take a look at my activity report here. Okay, so there's on one thing called memory pressure. You don't need to know what's memory pressure. Memory pressure is should be introduced at mountain level. Yeah, they will measure the pressure. If your pressure is too high, they will compress certain kind of memory. Okay, we test it really powerful. Maybe later I test you guys what is the pressure. Okay, but don't be out of pressure. Care about this guys. The swap that is used, okay, is there. Now, what happens if we have to swap back the memory? Okay, then my machine is okay. You know, my machine is running on SSD. Okay, if your machine is running on hard disk, 5,400 RAM per minute, sorry, yeah, you will have a very big headache. You are copying things back, okay? So the context switch actually also involves this kind of area, not just copying the backup of the register set back to the CPU. It will also trigger the memory that is on the swap. Now, what is the problem? That means that there's a big problem. It's not talking about the usage. Okay, I don't know what is the problem that you're using, but many of the design or many textbooks tell you what about this thing. We want to minimize the number of context switching during the execution of the scheduler. Okay, and what is the meaning? There are more meaning than just swapping from a swap to here. Okay, if you know a bit about CPU, okay, we are trying to minimize several aspects like both switch core. Originally you had core 1, okay, on CPU 8 core 1. Then next time I put you back on the CPU, I will try really hard to put you back to the CPU 8 core 1, but not core 2. Okay? If you know what is L1 cache, then you will understand what I mean. How many of you know what is L1 cache? Only what happened to this class? Are you guys in computers related things? Okay. No one knows what's L1 cache? You don't buy CPU? Oh, okay. Yeah, L1 cache, okay, is a cache per core, okay? Cache per core. Do you know what is a cache? Yeah, it's not, some professors tell me that you should not pronounce a cache, okay, because it's French. It should call cache. That's what professors tell me. This is the French, okay? So, Cache. How many of you don't know cache? And then you know what is cache is? Suddenly I say L1 cache is the custom L1 cache. Yeah, L1 cache is a for a core we have a piece of memory. Okay? Now there's a problem. The problem is very close to this picture. Every core has its own cache. If you try to switch one process originally in core 1 and you put it back to core 2, basically the core 2 L1 cache don't have the copies of its memory in its L1 cache. What should you do? What should you do? You don't need to do anything. Okay? When that process goes to the core 2, okay? Not core 2, okay? The core number 2. Okay? Then you will insert all the things back to L1 cache. Okay? And how about core 1? Eventually you will invalidate all those useless cache. Okay? So this is another aspect of why we try to minimize the context switching, or I should say, be more specific. Don't change core, don't change CPU, even don't change some of the memory usage or something like that. So context switching is very hard to explain context. And whenever you want to try to understand more, don't read any textbook. All textbook usually just like me will give you a high level concept. Okay? If you want to know it, there are several books, okay, which are quite good. What are they? I don't want to say about this book, but this is the only one that I can find. Is it on my desktop? Let me see. No, it's not on my desktop. Okay, so there is a series of books written by Microsoft. Okay, talk about their Windows core kernel development, kernel design. Okay, you'll find part 1. Okay, I remember this. It's three parts. Okay, you can take a look at the scheduler part and how they describe their context switching. Okay, Linux also. Mac also have one. I can't remember the name. It's called Mac. Also again, it's called internals. Mac OS internals. Right, this book, very old book, okay? It's also talk about when context switching comes, okay? What is the design principle of Mac OS in order to reduce the problems that I just mentioned? Okay, so context switching is a very big topic, and in the elite class, okay, I will show you the code, show you the real working of the context switching, okay? But I cannot touch too much, okay? It depends on you whether you want to read more or not. Okay, so it's about context switching. There are books on it. Okay. Now, after we know that there's context switching, then we know, oh, we have to switch from process to process, and the control is not by you. You are the process. It's not by the clock itself. The clock only gives you a signal that hey, we have to stop. The main role is done by the scheduler. Okay, and the scheduler is very passive. What is the meaning passive? He cannot mandate that, okay, in this computer, I only accept sorting program, okay? I only know how to schedule sorting program. I don't know how to schedule program that you solve, okay? The solve is a bad guy, right? Killing one process, okay? No, scheduler is very passive. They don't know how to adopt to the real case, okay? Later I'll tell you what is the meaning here. Okay. Basically, when we talk about the scheduler performance, now this is an old way to look at it. Okay. Linux, I remember 5 or 4 years ago, they had a new type of a scheduler that looked at the problem in another way. Later on, I can talk about it for a while. So we have two guys, two main family. One is called IO bound. IO bound process. What is IO bound process? Process that read files. Process that access your GPU. Process that the camera can be used, but the computation is not on the CPU side. You call for processor, you call hard disk servers, you access USB drive. Okay, that is called IO bound. IO bound guys are bad guys. Okay, what are they? They go to the CPU, execute very few code, Those codes is actually to set up what are the device I want to go, what are the service that I want to access, then call the CPU that, okay, please take the out, right? Because I already fired the request to that GPU, to that USB drive, I will step aside and wait for the call to come back. This is the most bad guys, okay? Why? You waste the CPU power to execute something, and actually you will go away, okay? Then this is the very special signature there in this process. You will find system time is much bigger than user time. Now let's take a look at whether we can find this kind of process. I don't know. This is a real life show. Okay. I don't know whether we will find such kind of process. Let's go to our department. Oh. And I will go to the Linux, maybe 18. Oh, what? 17? Oh, okay. No process there. No one execute anything. Yeah. 16? Whoa. No one. Oh, I found Kelvin. 19? Wow, department guys are very lazy, huh? No one is working. Okay, I go to HPC one. HPC, no HCP. It's a high performance computer. Right, we've got someone. Oh, I found Jimmy and his supervisor. Okay, so these are the two guys. Now, where do we look at? Okay, we cannot look at a per process CPU time with someone running MATLAB. Okay, how many percent? It means that it's taking up 10 cores. Okay, yeah, it means it's taking up at least 10 cores, maybe the 11 cores also. Yeah, this is the things that I want you to look at. Okay, yeah, it's gone again. So maybe I quit and then highlight. Okay. So you can see this guy, okay, actually consuming many things. But look at the report here. Look at the report. This is a system-wide report. Aggregated report over all processes. You only look up these two columns. Other column you don't need to look up. This is idle. This is the user time globally. This is the system time globally. 70% of system times means many already. Okay? Usually you will find a normal machines with very small system time. Let's go to some idle machines. Okay, idle machines. The next two. It should be idle, right? This guy is idle. So take a look at the system time. 0. Usually it's 0. Any machines should be a little bit busy. My machine should be a little bit busy. Okay? Yeah, I don't have much things. It's 0.1. Okay? So usually the system time is very small. My Mac machine. I typed the wrong key. Mac here. 4%. This machine has a higher system time because I'm doing the recording. Okay, I'm doing recording. That's why I'm accessing hardware. Okay, so the previous report is this time is lower. Previous number is 17. 17 is very low. Okay, and when we find some signature here, that means that there are some I/O bound processes running. I guess the HPC, the same why there is I/O bound machines. There are processes accessing GPU, running on GPU. So it uses some of the kernel code to copy memory to the coprocessor and ask the coprocessor to run. So it takes some time to copy the memory and get the results. Okay, so this is I/O bound, and the simplest I/O bound process is LS, right? LS. You know, how many times LS will use memory? No, right? Basically no. Or very few, I should say no. Right? Go to the hard disk, look at the data, and sort the output. Okay, the sorting is memory based. Okay, and after the sorting, clean that out. Mostly system time more than user time. Okay, networking program also, because that program involves many I/O calls. The I/O call is to ask the hardware for network card for your servers. Okay, and another way, we have a CPU bound process. CPU bound process is easy to find. Who are they? The CPU resources that previous show, 1000% of CPU usage, that guy's CPU bound process with a high user time and higher than system time. What are the things that you will think of some AI program? Usually AI program is a memory-based search, okay? You create a piece of memory, you create all the states, but all are inside the memory. Most of your data structure assignments, yeah, I cannot think of too much, okay? But let's say the sorting, okay? In the beginning, you will read the input, but this just once. And then you do the sorting, spend more of the time in doing sorting, and by the end of the program, you clean it out. Okay? So this is a case for user time more than system time. Alright? So this is a two classification. Usually we will focus here. We will focus here. Because this guy hard to predict. What they will use the CPU? Let's say I'm a scheduler. I know that this is an HPC. Okay? I predict that this guy needs more CPU resource. Maybe I set up the clock interval longer so that you can run for more time. But so happen that this naughty guy is not even CPU, it's a GPU. Okay? Then GPU is not CPU, right? GPU is a hardware card. Okay? Then waits. Okay? So this guy is more easy to predict. So later on we will focus on this CPU bound processes. Alright? And there are hybrid, this kind of thing, right? You have a process that will switch around different tasks. Let's say the AI strategy, you are doing memory search. Then some of the time, okay, you may spend over the network to get the input in the output, send outputs, okay? And the next is a video rendering. If you're doing a 3260 with graphics course, then you understand why. You spend a lot of time, okay, in constructing your 3D world, and another kind of one, okay, 50-50 time. Another 50 time is to render the data to the hardware, okay? So this hybrid, but we don't focus on one process. We usually implement in threads. Threads, when we talk about in part 6, is this course, okay? So, if it is CPU bound or I/O bound, it doesn't matter. It doesn't change this rule, okay? So what are the rules here? Let's take a look at column 1. Okay, column 1 talks about 4 events. What are 4 events? When a process creates, okay? This is a more detailed picture over the previous, I said very important picture, right? This may be one of the time that you will kick the scheduler, okay? Kick it, yeah, move. Why? I create a new guy. Okay? So it depends on the system implementation. Let's say our system implementation is fork, don't invoke scheduler. So what will happen? If fork don't invoke scheduler, we will create a new process, insert it into the end of the process queue. Then you will always have the parent continue to run. Understand what I mean? If I create a process, the fork system call, after the fork system call, this event on the implementation of the scheduler, it won't care about this. Yeah, don't kick me, okay? I will serve fork system call. Then you will always observe that parent run first. If there is a system implementation is like this, when you create a process, you will kick that scheduler to run, and the scheduler says, okay, I'll reschedule everything. Then you will have maybe 50-50 chance that you will find process parent run first, maybe 50% chance child run first. And then we will have another kind of system. Maybe the another system is like this. The scheduler favor young guys. Okay? When we do the schedule again, the newly constructed program, the child is the youngest. I always schedule him first, because it's always the youngest. So then you will find a system with child run first. Okay, but I seldom find this kind of system. Usually we will have the first two. Okay, so this is one of the events that the scheduler will get kicked. Okay, some of the events I already talked about it. Termination, IO call, or finish of IO call, but it is very seldom. Very seldom that the finish of the article will trigger the schedule. Alright? Why is it very seldom? Because you know you have other process, okay? Unless you are the only guy, in the system that is ready, then you are forced the scheduler to choose you. Okay? But very seldom. Alright. Last time we talked about this schedule, okay? I don't cover it anymore. Okay? If you want to know what is it, try to call it or try to read the main page called schedule. And we have two classes of process scheduler. The process scheduler is how to pronounce it is preemptive. Okay? The non-preemptive scheduler is very, very uncommon now. Okay? In the very old days, you can pick up any one of the OS textbook. Usually the first chapter is talk about OS history. Okay? And you will find this kind of thing, okay, 1968, doing the non-preemptive scheduler. So what is the meaning of non-preemptive? The previous example that I talked about. You create a new process, and that new process creation with the enqueue activity to the process queue, not invoking any scheduler, right? We call it non-preemptive. You won't preempt, you won't stop the original running process. Okay, preempting, interrupt it, stop it. Okay, so non-preemptive scheduler, and the non-preemptive scheduler only works on the following two rules. Let me highlight them. Okay. So when a process runs, okay, either it voluntarily wait for I/O, they will leave the CPU, and because it's non-preemptive, right? I have to wait for you to go, right? Okay, or it voluntarily release it. Either you call it schedule or you call it set. Okay, then it will go away. Okay, so this the case that you will go away. Okay, if a process is purely CPU bound, so this is the most funny thing. Okay, in the unit class, I will ask you to do this. Okay, set up a CPU bound process. Okay, and try to change the scheduler so that the scheduler always favors this guy. What will happen? If you guess, even the scheduler of this guy didn't do anything yet, okay? I just say I want to invent a system, okay, that always favor CPU bound process. If I have a while one loop, I will try to give all the CPU attention to the while one loop. And do you know what will happen at the end? Very interesting. That machines serving while one loop, right? Then it will, as if it is hanging there, it's become a frozen system. Okay, unless the CPU bound process dies. Okay, so very interesting. So that's why this kind of machines, okay, according to that professor called teach me the word cache, okay, the same professor. Okay, that professor is already retired. He told me that inside this kind of old non-preemptive scheduling machines, there is always a system of meaning. Okay, so do you know what that system of meaning is doing? Very interesting. They collect jobs, okay? Let's say this guy again, okay? Give me a job, okay? The job is programmed, loaded in the program, and he don't just send me a program, of course some data as well. He also gives you one thing. Please estimate how long your program should run. Understand what I mean? Because that machine is non-preemptive, other process cannot jam in and ask it to give up the CPU, okay? So you have to tell me, let's say your program says, 5 hours. Then I will kill your program after 5 hours, no matter you have output or not. 5 hours gone, kill. Okay? So this is a very, very old type of machine, okay? And I don't need to say the pros and cons because it does never exist in your knowledge. Now, the nowadays things we call it preemptive scheduling. Okay? Preemptive scheduling usually works like this. If I create a new process, you will always pick the scheduler to run, and the scheduler will find a guy to schedule. Okay? And this is based on this interrupt, clock interrupt, hardware interrupt. Okay? And that's why I don't need to say too much. Okay? So there are several policies. This policy is embedded in the scheduler. First of all, we have our fairness. What is fairness? Yeah, fairness is very hard to define, right? Even nowadays, have you heard of an issue called net neutrality? No. It means the ISP, when the ISP is treating you fair. Okay? It's a similar topic here. What is a scheduler's fairness? No one knows, right? You are a CPU bound process. Okay? I give you 10 context. Okay? You are IO bound process. I also give it 10 cocktails. So what is the feeling? The feeling is the IO bound process, enough, 10 cocktails, because I only need 2, and then I go to wait for IO. CPU bound process, 10 cocktails, I cannot even finish one layer of my for loops. Okay? So this is very hard to understand or very hard to explain. Usually what we will consider is every process given the same amount of clock text. That is fair. Okay? And later, Linux community think that it's not the way. It's not the way. Why is that? Why is that? Let's say I'm having a video player. Okay? So when the video player gets triggered, when you play, every part of the system is actually involved in that activity. Right? What is that? You have outbound process retrieving the hard disk because you need the data of the video. You so happen that you play 4K video, okay? You start with 4K video over very old system. Then you don't have a hardware accelerator, okay? You have to do what you guys call it? You call it software rendering. I call it in English, right? What is it in the Cantonese? Something like that, yeah. So you use the software to render it, okay, 4K video. So this is a CPU intensive job, okay, CPU bound process, and at the same time, you don't actually aware of it. There is a video rendering engine in Linux. If you're using Linux as a host, Linux as a host here. Yeah, XORG. Oh, yeah, the XORG. So when you run some video playing or video games, you'll find that XORG CPU rising. Yeah, the CPU resource rise, okay? Because it is also a process that tries to display the output. So this set of things together, you cannot say anything about fairness. Why? You give all the resource attention to the XORG, sorry, you don't have anything to display. Because other things cannot serve you. You serve the software rendering machine, sorry, you don't have data from the hard disk. Right? So what is fairness? I don't know. Okay? I don't know. So Linux community have invented one new trick. They group the whole set of process as a process group. We call it a process group. And the name, if you're interested in it, yeah, some people already thought, something new. C group. Okay, so kind of new for 4 or 5 years. They try to group them as a set of processes, and when the scheduler treat this batch of processes, they will give kind of, okay, more or less fair treatment to them. Okay, and one of the comment is from a Linus, okay. Linus said that, well, this is a very important improvement in the scheduler. It gives interactive processes like the video player very significant boosts in performance. Okay? So the fairness, we don't know, okay, but in our course of very classical, even some of the people like scientific people, okay, they quest for performance. So they will think of CPU bound process, and in the CPU bound process, fairness means every process gets similar amount of CPU attention. Okay? Next, policy. Policy is simple, right? Do you think that you have the same policy with the administrator? Do you think that the administrator run a loop is slower than your process running a loop? Yeah, usually no, right? The roots, okay, can change the priority. Okay, you see me changing priority last time. I changed the priority in running a while one loop. Okay, don't mention the while loop. I find that when I go back to the office, I drain all my battery because I forgot to kill it. Why not? I'm running on power. Okay. Yeah. Okay. But yeah, that one. Okay, I can increase my priority, but the root can raise the priority. Okay. So this is policy enforcement. You have to enforce, but not talking about fairness. CPU I/O balance. Hard to say. What does mean hard to say? The balance and fairness, and just mentioned about the C group, is you kind of put these two guys together. Okay, I have some tests outbound, but eventually I will shift the data to a CPU bound process, and then I want these two guys to run as if having certain progress and their progress because they're related. Okay, I want to jail it in the same group. Okay, and well, we have this kind of thing. And in our course, okay, I just give you an incentive to understand the CPU balance process. Okay, by looking at a different kind of a scheduler implementation. Okay, so let's have a break. I know that there's a tough. Every textbook, okay? Every textbook has this problem. They talk about the algorithm that will be covered, and the algorithm itself you already know what it is, okay? You already know when you don't know there is a name and there's a real implementation inside operating system. Now, first of all, what is the input? The input I usually call a set of processes or a set of tasks. Okay? And each task they have its own arrival time, arrive to the system, and CPU requirement. So how many CPU you need to run before it stops? I mean, usually in terms of units, maybe top 10s or maybe seconds, this and that. Okay? And we call this kind of setup an offline scheduling algorithm. So what is the offline scheduling algorithm? It doesn't mean that we don't need that one. Oh, probably in is on the line, or it's on the line. It means offline algorithm means the setting is fixed. I give you the fixed setting. You can use only one of the things. Then you can give me optimized user, optimized time in order to finish all things. Every process happy, okay? Online algorithm is our engineering faculty and data system. Online scheduling algorithm, okay? That scheduler sucks. You know what I'm talking about? Huh? That pair of lips, okay? Now this is one. You know, I always say that this design must have a non-scale to be put in the wrong position. Okay? Always is they used to minimize our experience, minimize our bad experience, now become maximize our inconvenience. Okay? Yeah. There's an online algorithm, and online algorithm is proved to be anti-hot. Later on, you want to tell me what is anti-hot. Okay? Yeah. It means that we need exponential amount of time in order to understand that, hey, I find an optimal solution. Okay? So, we are not present for optimal solution because the scheduler has to design something very fast. Okay? We don't need to calculate all until the end of this year. I know, oh, this is a set of processes. I know how to schedule it well, sorry. Or you say have already press Control C. Okay? They don't wait for you. Okay? So, and one more thing about this black box. This black box, later on, someone wants to talk about this, okay? You will never know a process CPU requirement. You will never know. Okay? Do you know when you write a for loop, okay, you write a for loop, you know how many exact CPU time you know? You will never predict it, right? I will always say that the order is kind of fixed, but the exact amount we don't know. Okay? And this is from an analysis of the algorithm. And one more thing I will tell you is about the key part of the talking problem. But yes, okay, this is the theory talking about whether we can understand a program will stop or not. It's a talking problem. Okay, so the talking problem tells you that you will never know. Okay, you will never know a program will stop or not. So from this point of view, the whole chapter is a bullshit. Okay, you cannot estimate it, and you tell me to estimate it. What is it? Okay, yeah, but this is some guidelines or some guidance that I want to tell you before we go to analyze it. And what is the output? We need two important outputs. Two important outputs very easy to understand. One is turnaround time, one is waiting time. So how to experience, you already experienced it, okay? Who never go to package shop in this group. In this group, okay? This group has a problem, okay? Yeah, you never know. Okay, everyone go to there. So what is turnaround time? The turnaround time is the time that you enter the shop, start queuing until the time that you can go out the shop. This is turnaround time. What is the waiting time? The waiting time is the time that you start joining the queue and until you get served. So why we have to separate these two things? seems to be, according to your experience in a parking shop, there's just very little difference, right? The time that I need to stop and the time that I stand on the queue to truck service. The difference is service time. Now, why is that? Because it's a very, very personal. Okay, for me, okay, I don't want to have a big waiting time, but I don't care about turnaround time. So what does it mean? I want to be served. Okay, I don't want to get in the queue. Okay, I want to go there and that guy served me for 15 minutes. I don't care. Yeah, as long as I get service. Okay, maybe I find an entire parking shop. So I need 1 hour for this time. Okay, so this why there are 2 times, right? For other guys, okay, they will have a huge waiting time. Not for me. Okay, these 2 are very important. Later on, you will see a different outcomes actually mentioned. I mean, not mentioned, but they emphasize on these different things. Okay. So one is time that you get in the shop, start queuing and leave it. Another is about actually it's measuring the happiness. Okay. You are happy when you get served. You are not happy when you get in the queue but not being served. Okay. So this is the happiness. And we have several outcomes. The first one is easy. Okay, what is the first one? Parking shop, first in, first out. Right? First in, first out. You first go in, okay, unless there is I don't know, some hidden people just pop up, okay? You say, oh, I will stay there. Okay, I will fly there. Okay. Yeah, okay. Then another is imaginary algorithm for some stuff first. Why is imaginary? It actually is like this. This is your nowadays scenarios, okay? Solid top first means that you estimate all the jobs. We know that job takes minimal amount of time to finish. Then you will do it first. Similar, is it your assignment scheduling algorithm? Yeah, you estimate that assignment takes a minimal time to do it, but usually the estimate is wrong. Yeah. So that's why I said it's imaginary, okay? Never implemented and never works. Never works because your estimate is wrong. Usually you think, that assignment doesn't need to do programming. It should be the minimal task. No, you have to put too many text box, okay? Many paper, and even Google a lot, then you do how to finish it. But for the programming, maybe the amount of time is quite short, okay? So there's also first round robin. Round robin is nowadays implementation. It means that I have 4 quarters here. I've touched this guy for some time, and then this guy go back. Okay, this is round robin. Okay, but you do one. I remember some people will do round robin. Okay, because they don't know how to do assignment. Okay, so you touch this. I don't know. Go to the next. I don't know. Go to the next. I don't know. Okay, you have to finish it, right? So they go back. Okay, and do the cycle again and again and again. Okay, this is round robin. Priority scheduling, not about assignment, okay? I will skip this because it's not quite interesting. Okay, it means that basically you have different priorities over your assignment, okay? Let's say that your LOL priority is higher than your assignment. Then you will finish it LOL first, okay? And it's preemptive. Okay? Your friends tell you that, hey, let's play. Go ahead, okay? And that's why it's preemptive, huh? And usually your mother's code is not preemptive, they don't preempt you. Right? Your mother calls it, wait. Okay? Multiple kill is a real implementation with priority, and at different priority, we may have different scheduling way. Okay? In real world implementation in Linux, we have priority, let's say a very high priority, we'll implement FIO, so because they are very important, okay? I don't want people to get interrupt me, so I will have the first guy join the queue to finish first, okay? And for other queues, maybe the queues for you, not for the administrator, will be out, okay? And there are many implementation of out, some with weights, some with other control to alter the order. Originally is 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Maybe we will alter it based on weighting. Maybe this guy has go away to go to IO call. Okay, his IO call is actually go to the toilet. Okay, and come back. And maybe I compensate this guy. Okay, I give him more execution time. Okay. So this is the difference, and when we go into it, very easy to understand, right? FIFO. FIFO means that let's say arrival time of P1 first, and P2 and P3. Okay, and it's hard code, okay? Hard code and high code CPU requirements like this. Okay, so why I think of this implementation, you don't need to take look at the number first, okay? This implementation is, I somewhat experienced it in KFC. I am the P3. This guy is the one by pocket. I hate those guys. Okay? You never experienced that? I always pray that, okay, the one before me don't buy pocket. Okay, then, oh, so happen is buy pocket. 10 minutes, okay? So this is the, you know what I'm saying, you don't go to KFC. Or maybe go to pocket shop, okay, that guy actually buy $300 steaks. I only buy a box. Can I interchange the bro with you, okay? Yeah, let me pay for it, okay? And I even pay you more, okay? No, you cannot, okay? So because the system in pocket shop is FIFO, okay? Although it is an FIFO original, already very good, way better than here. Here is only one CPU, single queue. We have a single queue, multiple CPU in pocket shop, but those CPU are too slow. And will get wrong. And even get preempted, suddenly we have there is a model that is go to suddenly, oh, go away, one CPU is down. And you never experienced that. I hope, now it's my turn, that CPU is down. Yeah, okay. Then the computation is easy, right? You just count the time that when you arrive at the system until you get served. That will be the waiting time. And the time you arrive at the system and then go on the system is the turnaround time. So we have a little bit different. Okay? So this CPU requirement holds are free, so the difference here is also free. Right? The time I go to the shop, I get start queuing until I get served, waiting. So the waiting time is actually the measurement of unhappiness. This guy is very happy because one is go to the queue is get served. Okay, you never find it bored. Okay, let's imagine that you're going to KFC. Okay, you stand there looking at that guy, you don't feel any unhappiness. But when you are this guy, you are getting very unhappy. Okay, so the measurement is like this. If we are able to interchange something in this way, I just swap the queue. Okay, become a different arrival pattern. Then you will have much better happiness. Much better happiness. Originally is 16, now it becomes 2. And also the turnaround time because the first two guys can leave the shop early. Okay? And it's really implemented, the FIFO in a Linux with a very high priority scheduling role there. And then usually for, let's say, all the things that you do. Journaling file system, let's say, there's a journal. The journal is actually a very important thing, and it will enter the FIFO scheduling routine that please schedule me first, okay? I'm very important, okay? Then it is implemented, yet when we know that we can reshuffle it, which is good, but in a real world we cannot reshuffle it, it's always FIFO. Now, let's say if I can reshuffle it, okay, yeah, this is a KFC scenario, okay? If you don't understand it, read it, okay? Or you go to KFC where the closest one should be in shopping, so the experience, then you understand what I mean, okay? And then SJF also out of date. Some people really want to implement it, but they can only implement it based on the fact that we know the CPU requirement, just like approximately an hour ago. I said that there is an old days implementation that administrator will collect all the jobs, okay? And when they collect all the jobs, then they will process it in a batch, and we can do so in this SJF implementation. But without this, nowadays system, we actually don't know the CPU requirements, so that's why starting from this lecture onwards, okay, don't do assignment using SJF, okay? I give a better implementation, use deadline first. Yeah, deadline first implementation. Much better, right? At least you get something done, right? The SJF may end up you don't have anything get done. Okay. So this is the SGF. SGF is easy. Oh, what is that? This is a set of processes, okay? And I'll indicate whether you will finish executing or you're still there in the system. First of all, we have non-preemptive implementation. So that means that no matter the new job arrives in the system is having a lower or lowest requirement, we don't care of. We don't care of it. Okay? So the first start is a 7, and because it's actually non-reactive, until this guy finishes, you won't touch other processes, although they already arrived later, 2, 4, 5, they already arrived. And then that's why we finish it after 7. Continue, now we will sort the arrival time, or stop here. Sort the CPU requirement. If we sort the arrival time, then means it's a typo. We sort the requirement so that this guy will execute first, as if I don't let this guy down, okay? You are find a small topic flaw, okay? I give you have a higher chance coming in, okay? And then I give you a higher happiness, okay? Or smaller unhappiness, I say. Okay? Then you will continue to do this, and this is the result. Non-preemptive. And the preemptive, I don't need to show the calculation. I mean, this is for you to double check, okay? And the preemptive scheduling, usually when I say preemptive, I will set some rule. The rule is like this. The scheduler will always step in whenever there is a arrival. You can imagine what's an arrival. Fork system call, okay? When I fork a new process, create a new process, I will, have an interim or have a call of a scheduler, or I should say the scheduler will step in. Then we'll measure the new process CPU requirement, which is not important because we know that I only have to do it if it's not well. And then when we start executing the first process, okay, you expect that 2 unit time later, it will get preempted. It will get preempted. So when preemption comes in, the remaining CPU requirement is 5414, the 14 doesn't exist yet because this time is 02. So P2 will get the chance to run. Alright. Then another schedule setting moment will be time to 4 because a new process comes in. Now we have the requirement rest, left there 1, 2, 5, so 1 will get execute. And 1 was unit time later, I will have this termination as well as the new process P4 comes in. And so on and so forth. So this is easy, right? You can click on a popcorn to see, by the way, to complete it. Okay. My animation is page by page animation. Okay. So if you print it out, then you will just like print all the themes. Okay. Yeah. So I already write a tag here. Huh? Okay. So this is the ending results. Now, what is the difference? The difference is this is the calculations. I will show the difference in this table. Difference is like this. With preemption, we have a better implementation of better results in terms of our execution and the number of context switching, although because it's preemption, right, I will switch more, okay? And think about it whether you want to implement it in your assignment scheduling algorithm. Yeah. Think about it. This is kind of good, right? If you estimate the things correctly, okay? And the turnaround is also good. Okay, you will have a better sense, not a sense, just a force feeling. Okay? Oh, I have the assignment finished in average earlier. Yeah. Who cares? Okay. This is another thing. Okay, usually in assignment scheduling, you have a better idea now, okay, because you are getting busy. Okay, and whenever you context switch, you have some overhead, right? Yeah, what is overhead? What was the thing that I was doing? Okay, or previous, what was my progress? Okay, I forgot. Okay, or I skipped the lesson. I have to read the video or read the notes again. Okay, you have some overhead. Yeah, don't care about this because the SJF is wrong implementation. Now we go to something real, which is important now. It's a round robin. Well, I will say that I will have some rules first, some vocabulary. The vocabulary is, don't ask here. We call a time interval that originally assigned to a process quantum. Okay, and flow is quantum. Okay, quantum. Okay, don't ask me why it's called quantum. Okay, so it's called quantum, and when quantum moves up, this is real implementation in most of the operating system. We will leave the quantum value equal to 0 until the entire set of processes go to 0. So this is a very good indicator that I already scanned through the entire set of processes which are ready. Then I will recharge, okay, all process to some value. And in this example, I choose the value that recharge will be the original quantum that I give to each process. Okay? Understand? Yeah, very easy. So we will have the following rules with the tables, just like the SJF. The SJF table is again here. I will show it. Okay, you can click the slides again. But I will go to show the moment that, let's say I use on the pointer here, on the pointer, use up. What is going on here is I will have this guy terminated. This guy has more than 2 requirements, so it's still alive. This guy is still alive, but I will continue and recharge. Okay, here again recharge. Okay, this animation is a little bit stuck here. Okay, and what is the ending result? Let's skip to the ending result. So the ending result is something like this. I have the contrast here. The contrast is out is champion. Yeah, from the bottom. Okay. Most waiting time, very bad. Most turnaround time, okay, even more awful. Most number of context switching. Okay, so but it is originally the basic implementation of the modern operating system. So what is going on here? It's about responsiveness. About responsiveness. So what is the meaning of about responsiveness? If you still have experience, still memory, okay? I don't expect you are still running XP, okay? You still have memory running XP, then you understand why it is. When you click on some button, you want to launch some window, okay? Windows is like that, okay? They are so arrogant, really arrogant. I don't give you response, but I'm working. Understand what I mean? Yeah, the blank, those guys pop up, the blank windows pop up, okay? So I don't tell you, what is my progress? I just tell you I'm working. Don't shut me down, okay? Don't press control anything, okay? Yeah, I'm working, but you sense that it's working, okay? But no indicator, okay? This is the thing I said arrogant, really arrogant. Don't touch me, okay? I'm working. A Mac is a little bit better. At least it shows the spinning before, okay? Yeah, it's something spinning. Oh, I know you're working. Okay? Yeah, essentially about this kind of responsiveness, when we have a very high number of context switching, basically means that every process may have different chances to get on the CPU, so that you won't find the system so laggy. Yeah, imagine it's like this. You have 10 processes. Every process needs approximately, you can consider this infinite, okay? Infinite amount of CPU resource. Then every time I put a CPU is only running for 1 second. Then what is the aggregate effect? The aggregate effect is you have the process A running. Then you have the remaining 9 processes have to wait for how many seconds? Every time it's 1 second, approximately a long time, right? More than 5 or 6 seconds. Maybe some processes have died because you kill it, so and so forth. But you have a very bad responsive experience. Now in reverse, let's say I increase the number of context switching in a given amount of time by having a smaller quantum, then you will find a process move for a bit, and then another process move a bit, another move a bit, and in the aggregate experience, you find the whole system is smooth, but slow. Understand what I mean? It's kind of very uneasy to understand. something smooth but slow. Yeah, something work but not responsive. Okay? Yeah, you can experience that if you have a, some people say that in using Mac, okay, you're given a same configuration with Windows or with Linux. Linux, we finished something earlier. Mac finished something earlier. Which we finish something earlier, usually it's Windows or Linux. Mac is they give you a very good responsiveness, but because of this, you have many context switching, and you will find it smooth, but you will find it longer time until you finish the job. Okay? Yeah. Do you get my meaning? Yeah, it's kind of a not philosophical, but you need some imagination. Okay? And this is nowadays system. Okay? The nowadays system actually aim for interactiveness. Okay? Because we launch many interactive jobs. Okay? Better switch processes as fast as possible. Okay? So, and oh, there's a joke that I want to share with you. Okay? I remember. So what is the joke about? Okay? You guys are too young. You don't know what I'm saying. Let me show something first. Yeah, anybody know this? Anybody know this? Everybody that's seen this know, but you see the IE version. You see the IE version, the turning Earth, right? The E and then become an Earth, E become an Earth, okay? Yeah, this kind of thing, okay? Of course, why I show Netscape, Netscape stop this first, okay? And what is the reason behind, okay? In the old days, okay, we have a slow CPU. You spend some CPU time to show this. Okay, are you going crazy? No. Okay, it is a responsiveness. It is about the UX, user experience. Okay, you tell the user that I'm working. Actually, I didn't start anything yet. Yeah, I'm working. I show something. Okay, then don't touch me. Okay. Yeah, there's a joke. It's about responsiveness joke. I'm working, but I didn't do anything. Yeah, as if in your home, okay, you tell your mother I'm working. Okay, but actually I'm playing. All right. Another observation, kind of fair to all processes, kind of. Okay, because we assume that every guy is a CPU intensive guy, so you will get the CPU attention from time to time. So this is good, but whenever you have an I/O bound process, then you have to think about this question. What is the fair treatment? I'm now implementing a real OS, not just an imaginary scenario that I'm writing in this PowerPoint. I want CPU intensive job to go with the CPU, no problem. They will suck up all quantum and everyone will do the same, then I will be charged. Very easy scenario. Now I input outbound job now in the system. So what is the outbound job behave? Their behavior will be very different. They receive some quantum, okay? I don't know amount, but they won't use up because they spend a little bit time over the CPU and then jump away from the queue. Go to where? Go to wait for your keyboard input. Go to wait for the hard disk input. Write to some device. Or wait for device response. Then when they come back to the queue, actually it will be a different scenario like this. The queue is kind of stable. Only change is this guy dies. Now we have this queue become a guy, not die, go away. But don't schedule me because I'm waiting for something. And then I will come back. Come back for what? Come back for your service because my data is already count. Okay, and make the whole scenario very, very strange. And when we face this change, how can I talk about fairness? Okay, so usually when we talk about fairness, I want to say that again. I will give every process the same treatment. Okay, if your system is, let's say your system is Xbox. let's say it's Xbox, okay, or PlayStation, then maybe you will give some priority or bonus that, oh, this is a process that going to your PSN, okay, to get something download, and then download doesn't mean anything, right? I can let this job to have a fixed amount of CPU of time, then later I will charge it a fixed amount. What if we are playing Street Fighter now, okay? There is a process getting from the network the action the other side is key in. This is a very important job. We should give it higher priority, and also whenever this IO bound process comes back to the set schedule queue, I may need to schedule it immediately. Understand what I mean? You just somebody put a punch button, okay? The punch is coming, should be coming, right? And actually you cannot know about this until you receive that packet from the network, and which is a IO bound process. Now that process should have a higher priority and should get the scheduled attention more importantly than rendering that punch. Okay? So fairness, what is fairness? We don't know. Okay? Based on your system requirement. Okay? And any modification, I just mentioned one in a PlayStation scenario. Okay. Later I can find I remember I captured a screen, but I cannot find before I come to the lecture hall. I captured a screen over the Windows internals. Windows, I remember this about Windows 2000 or Windows NT. Yeah. Do you know what's Windows NT? That is very old version of Windows. They says there are bonus for IO bound process. Okay? So I need to find out that capture. Alright. The last one. I hope that I don't want to bore you guys, okay? I don't want to rush through the entire chapter by skipping things, okay? So I will put it later, put it to Monday, and when we have a multiple queue scenario, we're actually talking about something real. This is the real architecture of a Linux scheduler. Okay, we will touch a bit, okay, what is the inverter of a Linux scheduler, and I will also talk about a bit over the capture that I mentioned before. Okay, so I think this is the time to end.